All right, thank you all so much for being here. Thank you for the organizers for having me. I'm very thrilled to be with you all today. I'm going to continue the theme of Dr. Sophia's brilliant talk on environmental beliefs. So I'm going to think today about this causal chain from environmental beliefs to some climate adaptation decision, and then to some measure of economic well-being that we all care about. And even though kind of theoretically we think there could be an important role for environmental beliefs, as Sophia was just alluding to, we actually know extremely little about what these beliefs are, where they come from, and how they might matter. So just to give you an illustration, let's consider the case of soil salinity. This is a big problem that affects about 30% of irrigated land worldwide, and is one that's been exacerbated by climate change. So the good news is that there does exist technology that can help mitigate this problem. So in particular, I'm studying rice farmers in Bangladesh. They can plant salinity tolerant seeds. And so in my sample, for example, at baseline, about 40% of farmers are already adopting this technology. But this technology is not Pareto dominant. And so that's going to create this important scope for beliefs. So just to walk you through that, let's consider this kind of 2 by 2 here. The rows are the type of seed that the farmer might plant. And then the columns here are the type of soil that that farmer faces. And so the great thing about these salinity tolerant seeds is that no matter how high the salinity gets in the soil, those seeds are still going to perform well. You're not going to kind of get a hit on your harvest. By contrast, these non-salinity tolerant alternatives will suffer when the salt levels get high. But at low salt levels, they have other features that might make them even more appealing. They might taste better, might be robust to other types of environmental threats. And so the challenge for farmers is that they don't actually directly observe the salinity of their soil. And so what they want to do instead is try to match the technology to the environmental conditions without being able to directly observe that. And so because of that, their beliefs about which column they're in, if they're in the low salt world or the high salt world, are going to really matter for their adaptation decision. And so what I'm going to do in this paper is try to kind of use that setting to examine the role of environmental beliefs. And I'm going to answer 3 questions. First, how accurate environmental beliefs are. I'm going to do that through surveys and fieldwork I conducted with about 2,300 farmers in Bangladesh. I'm going to collect information on their true salinity conditions using agronomic measurements, and then elicit their beliefs and compare those 2 objects. What I'll show you in a few slides is that there are substantial errors, both over and underestimation of salinity levels among farmers in my sample. Then I'm going to examine how farmers actually form these beliefs, where these mistakes come from, and why they might persist in equilibrium. What I'm going to argue is just one specific channel today, which is that in a Bayesian world, farmers are facing this identification problem, where they're trying to learn about salinity by observing how their crop performs. And so if they see, for example, low yield, that could be consistent with high salinity, but could also be consistent with a lot of other problems and things that might go wrong in the course of agricultural production. And because of that, it's going to create this identification problem, just like we're all familiar with in econometrics, and that's going to create these kind of persistent errors in equilibrium. I'm going to test that today using a lab in the field exercise, and then 2 quasi-random natural experiments to try to isolate how farmers are responding to different types of information. And then I'm not going to have time to get into this today, but in the last part of the paper, I examine how these environmental beliefs actually shape adaptation. And just to give you a sense of what that is, first I do an information experiment and I show that beliefs actually indeed matter. So if I change someone's beliefs, that has a big impact on their adoption of technology, in this case, these salinity tolerant seeds. And then I run a second experiment where I actually just provide and encourage farmers to use those seeds. And what I show is that whether or not you kind of appropriately match your technology to your environmental conditions ends up having big impacts on your profits. And I eventually kind of combine these results into a simple structural model to show that overall, if we could wave a magic wand and give farmers perfect beliefs, we could have increased agricultural profits by about 16%. But as I said, I'm not going to be able to have time to go into any of that.
So do they realize they could do testing themselves? Is this a permanent feature of the soil so that they would benefit a lot from running an experiment themselves and then act on it?
Yeah, that's a great question. So I guess two answers to that. There is some variation over time, but kind of in the limit data I have, there's about a persistence of about 80% year to year on what the right decision would have been. So there is kind of value on just learning in the short term. And I do see evidence that the farmers that have more land and are older have better beliefs. So there is kind of some gains from experimentation. There's not going to be basically any local market for direct testing though. And so that's going to be kind of one great policy implication of this, is that if we could just help farmers learn that, that would kind of be a big welfare gain.
And just a related question, how uniform is the salinity and like across the plot? I imagine quite like uniform, but or is there like lots of variation even within like one or two adjacent plots?
So I guess like the intra-village correlation is about 0.9, but it is true that like if you go to a plot that's really tilted, I've been to places where like one corner you can see all the rice plants are a little bit shorter because all of the salt is gathering in that corner. So there is some subtle variation by elevation, but in general, there's pretty high spatial covariance. And yeah, if we have time, I'll talk about how that kind of can create a hindrance for this type of market for information. Great. Great. Any other questions on the context? All right, so I'm just going to dive in then to this first research question, talk about how I'm measuring true salinity conditions, how I'm measuring beliefs, try to address some potential concerns you might have with that belief elicitation, because as Sophia just mentioned, it's a hard thing to do, and then compare those two objects. All right, so the way I measure true salinity conditions is with these electrical conductivity meters. So this is exactly the type of technology that doesn't exist really locally that farmers have access to, but I can show that they basically, you stick them into the ground, right into the plot, you can directly measure what the farmer's actual salinity exposure is. And so I do this kind of during repeated measurements over the course of the agricultural season. So this is one really great thing about salinity from this research question, is that I can directly measure really what is the key decision relevant piece of environmental information that farmers are using to kind of form their decisions off of, and it's relevant to their technology choice. But the challenge is that, as I mentioned, farmers don't use this technology, so they have no sense of the sensors. And so if I asked you how salty your land was, you probably wouldn't respond to me in the electrical conductivity units. So how I kind of overcome that when I'm trying to measure beliefs in a way I can actually put in a regression is I use this picture. So this comes from an experiment where the researchers randomized the salt content of the soil and grew rice plants. And so picture number 7 here is the rice plant that's grown without salt in the soil, and then one, this has the most amount of salt. And what's great is because I know how these researchers did this experiment, for any given picture, I can map back to what that kind of corresponding unit is in the scale of my sensor. So to actually elicit beliefs, I show farmers this picture. First, I just ask them, well, what did your plant look like last year? What do you think your plant looks like this year? This is just to kind of make it clear in their minds that this is not the main salinity question I'm going to be using. And then I explain exactly how this RCT was done, how this experiment was done, and where this picture came from. I let farmers know that I'm really actually trying to focus on their beliefs about how salty their soil is. And then the main question I actually ask is, if researchers planted the same non-salinity tolerant seed, like shown in this picture, on your soil, what do you think the crop will look like at the end of the season? And then I have farmers place buttons on this picture in accordance with their beliefs, not just one button, but actually 10, so I can capture their kind of full distribution. And this shows kind of what the median answer was. So the few potential concerns you might have with this. First, you might worry that people are, I'm telling them to answer about salinity, but actually they're answering about pests or something. I can see at least that's not completely what's happening here, because these beliefs really strongly predict salinity-specific behavior. So, for example, spraying sugar on your plots or planting saline-tolerant seeds. You also might worry that that picture from those experiments are just different systematically than what rice plants grow in Bangladesh. So, if all of the rice plants in Bangladesh are a little bit taller, maybe that's an issue. That's why I'm going to primarily focus on just comparing across farmers here, so those level effects won't be an issue. And then you might also be worried that it's not actually a level thing, but the slope. So maybe in Bangladesh, as opposed to that kind of experimental picture, as salinity goes up, the height falls more or less quickly. So the way I can try and get at this without having that equivalent experiment in the field is I ask farmers at Edline what their crop looked like. And then I also know from my sensors what their actual salinity exposure was. So I can compare those two things. The x-axis here is the true amount of salinity I measure with my sensor. And the y-axis is what their implied salinity would be, given what picture they said their crop actually looked like. What you see is that I can't reject that the slope here is 1. So in other words, for every true amount of salinity increase that I get, the implied salinity based on that picture also goes up by 1. So the slope seems to be the same. All right, so now I'm going to show you how these beliefs actually compare. On the x-axis here is the true amount of salinity based on my sensor, and the y-axis here is farmers' beliefs. If everything was correct, we would expect all of the dots to lie on this 45-degree line shown in gray. So this is what a bin scatter plot looks like if you just collapse across all farmers. And in fact, I can't reject here that the slope is 1 and the intercept is 0. But that kind of average mass.
Can you maybe elaborate a bit on like how important at baseline salinity is for like just understanding differences in crop yield? Of course, I understand that if everyone were perfectly adopted, that like the variable wouldn't matter anymore. But like, I'm just trying to understand from the perspective of the farmer, is salinity like first order, or like are there many other aspects of soil quality they should care more about?
In terms of soil, salinity is like probably the number one thing. There are, pests and floods and other things that farmers worry about, but salinity is, typically ranked among the top 1, 2, or 3 things that they're worried about. I'm not sure that answers your question.
Yeah, I mean,
It would be like nice to have something that's a bit more quantitative, but I'm not like in this literature, so yeah.
So yeah, I mean, I can show from my, I guess like one answer to your question is like in my seed RCT, right? If you correctly adapt, you have huge impacts on profits. So I guess that's one way to know that salinity does matter. Okay, great. Any other questions? So yes, as I was saying, on average, the beliefs look correct, but there's a lot of heterogeneity. So now these gray dots show what the raw data look like. And in particular, you can see that most people are actually far away from this 45-degree line, in both directions. Now, of course, some of this is going to be noise and elicitation, both in kind of the left-hand side and the right-hand side, but I can show this is not just measurement error. First, there's very strong spatial covariance. So people in the same village tend to be wrong in the same kinds of way. Second, the farmers who we think should be better are exactly the ones who, in fact, are better. So it's the ones who have more land, more experience, whose neighbors say that they're more skilled. And then third is that the residuals here, if you take kind of a dot and you take the distance from that to the 45-degree line, that's going to be really strongly predictive of actual behavior here. So this is capturing something real. Okay, so hopefully I've convinced you.
I have one question.
Oh yes.
Do you have any sense of if there's a so there's soil salinity, and then there's also the kind of quality of water, that the drinkable water that they get, so the waters also directly can be saline. Do you have any sense of like whether that's more salient, or I mean they are correlated, but could that be a bigger factor in kind of deciding whether your conditions are saline versus the kind of the soil salinity itself?
Yeah, it's a great question. So if you ask farmers kind of how you learn about salinity, basically the most common answer is I look at how well my crop is doing, if it's growing well or not. The second most common answer, and it's about 20% of people, is that they taste the water or they taste the soil. And so you're exactly right that that's kind of one key clue that they use. Okay. So just one kind of note here is that you might think that before I was going to use just means. Of course, we measure that full distribution, so maybe people were actually kind of right on some support of their beliefs. It turns out that kind of more than half of people don't put any buttons on the kind of the picture that corresponds to the truth here. So this is not just about how I'm and what moment I'm focusing on. Okay, so hopefully I've convinced you now that there are a lot of mistaken beliefs in equilibrium. Why does this happen? So what I'm going to show you next is that one reason why is this is just a really hard problem. And so I'm going to illustrate why this is a hard problem to learn about, and then show you some evidence about those mechanisms. Okay, so the reason it's a hard problem to learn about is that even if you're a perfectly rational farmer, so you kind of are Bayesian, you exactly know how rice is grown, you have exactly understand how salinity might impact rice, it still might be hard to learn about. And the reason why is because all you can actually observe at the end of the day is how your crops grow. So you just see, did I have a high yield or low yield? And so though, because you're perfectly correct about the agricultural production function, that there's two things that might impact how your rice grows, the salinity, or for example, fungus or some other type of environmental threat, that both of which are unobserved. So both could impact and determine whether you get low yield, because they both manifest themselves in the same way, just observing low yield is not perfectly diagnostic of which one you face. So this is going to be this identification problem, and that's going to create basically this path dependence. So if I initially think that fungus is more likely, for example, every time I see low yield, that's just going to reinforce that belief. I'll never be able to really get out of that kind of trap of quote unquote of thinking that Thomas is the problem, even if in reality salinity is the issue. So with that kind of framework in mind, let me show you some evidence for that type of mechanism. So the first thing I do is I show farmers a bunch of pictures of rice plants where something went wrong. So for example, this photo on the left was a fungus, the one on the right, there was salinity. And I just asked farmers kind of the very first questions of the survey before we've talked about salinity. What do you think caused the rice plant to look like this? What I'm going to show you is on the x-axis here, the share of issues that are, for example, the blast fungus, the fungus pictures that weren't actually salinity, but people said were salinity. And on the y-axis is the share of salinity pictures, so like this photo on the right, that farmers correctly said were salinity. And what you see is this very strong positive relationship. So the farmers kind of have two big takeaways. One, there is disagreement about how to interpret these photos. Not everyone agrees on what the signal means. And two is that these errors are really correlated. So if you tend to think that salinity is an issue, you see salinity everywhere, quote unquote. And so once you kind of have something in mind, I think that this signal means salinity, you're much more likely to think that another signal also means. So now I'm going to show you some bit more causal evidence of this channel and examine ways that farmers are learning from real environmental shocks that they've experienced. So I'm going to consider two types of shocks that are particularly characteristic of climate change. One is what we might think of as subtle shock. In this case, as sea levels rise, they can contaminate groundwater. And then as you irrigate your land, you're going to introduce salt onto your soil. The other is a salient shock. So for example, if you get flooded with salty water, you're certainly going to notice that, and that's going to just mechanically dump a bunch of salt onto your soil. So what I'm going to show you today is that those different types of shocks are going to change beliefs. And so if you, for example, had a salient shock, that's going to make you think that salinity is more likely than if you had a subtle shock. And I'm going to be pretty agnostic on the reason why. You might, for now, let's just assume that, like, for example, you didn't even notice that your underground water got a little bit salty. The prediction of that type of framework I just showed you, however, is that that initial gap in what your beliefs are is going to change how you interpret new data. And so that's going to be kind of the key prediction that I want to test. So just to walk you through that logic, imagine two different shocks, both of which increase the true amount of salinity on your soil by the same amount, but only this salient one, which has a larger impact on your beliefs. So that's changed your kind of initial prior about what is more important. Then every time you see new data, you're going to differentially interpret that based on what your initial shock was. So that's going to be the sense in which there's some path dependency. So now I'm going to actually test this in the data. I'm going to use two different diffs. So the first is a triple difference examining a subtle shock. So I'm going to look at villages that are closer to the ocean, exposed to higher versus lower sea level relative to their normal exposure, and are exposed to saltier or less salty ocean at that time. So again, relative to their historical average. I'll be able to capture those two things with satellite data. The subtle shock is going to be, the salient shock is going to be a diff comparing flooded versus non-flooded areas that had, when they were flooded, saltier or less salty water. So I'll go into a second about how I'm measuring flooding. For the salty water, I collect data from river stations across Bangladesh that actually capture how salty the water is. I'll just flag that for kind of both of these designs, because all my variations come at the village level, I'm going to cluster my standard errors there. And so that's why in particular it was important that I sample over quite a large area. Okay, just a quick aside, since there's been so many talks on floods this week, want to talk a little bit about how I'm measuring floods. There's a lot more details in my paper on floods, and happy to talk more offline with anyone who's interested. One of the challenges is that we actually really don't have data on where floods have occurred. And so I'm going to walk you through how I use satellite data to try to fix that. So the first way is this satellite. This is from the Sentinel-1 space mission from the European Space Agency. And what's great about this satellite is that it's really high quality. So for example, just to walk you through how this works, it shoots radar, very light radiation down at the Earth, and measures how much of that gets bounced back. So for example, in my little cartoon here, the satellite's flying over Bangladesh. It's going to shoot radar down. When that radar hits things like trees or houses or anything that's not water, it gets bounced right back up. But when it hits water, that gets scattered, and so it actually doesn't reach the satellite. So this actually ends up working extremely well. So this is just a picture of kind of the raw radar that ended up reaching the satellite, and you can just exactly see in this village in Bangladesh where the rivers are and where the water is, because that's where satellite did not pick up the radar. The problem with the satellite is that even though it's amazing, it can see through clouds, it orbits really infrequently. So for example, in Bangladesh, it's only orbiting every kind of 6 to 12 days. And so that's going to miss tons of these flash floods that we know are actually really important. And just to illustrate that, it works well for a flood. This is the non-flood week day. This is the same week calendar a year later where there was a flood. You can just exactly see that there was a big increase in surface water. So the way I solve that frequency problem is that I pair this really high quality but low quantity data with pretty high quantity but low quality data, which is from the kind of satellite data we might be more familiar with in economics that takes photos of the Earth. What's great about that is that it orbits all the time. We get tons of images, but of course, when it's cloudy, you can't see the ground. And for anyone who's been to a flooded area in Bangladesh, it's often cloudy when it's flooding, and so that creates a selection problem. It's going to be pretty hard to overcome. So what I do in this project is I use machine learning to essentially recreate that high quality but low quantity satellite data using the high quantity but low quality one. And I can show that this works pretty well, and then by kind of applying that model out of sample, I can fill in all the gaps when that high quality one didn't orbit overall. So this allows me to measure kind of really local daily flooding for about 20 years. In ongoing work, I'm working to expand this for the whole world. Okay, enough about satellites. Now for some more on salt. So what I'm going to plot in this graph is a main interaction term from those diff and diffs. So that's going to be either closer to the ocean when the ocean is high and the ocean is salty, in the case of that subtle shock, or getting flooded with saltier water in the case of that salient shock. So the first result is that when you get flooded with a saltier flood, the amount of salinity that I can measure on your soil goes up. And that's just kind of from my sensor. When I look at that kind of subtle shock, I actually can't reject that those two effects are essentially the same. So both of these shocks seem to increase the amount of salinity on your soil by the same amount. When you look at beliefs, though, you see a very different story. So in the case of that salient shock of flooding, you see a much larger impact on beliefs than you do on the true amount of salt in the soil. And by contrast, I can't actually reject that in the case of that subtle shock, beliefs don't change at all. And so the key thing I want to take away here is that there's a differential impact on beliefs for two different types of environmental shocks that have the same impact on the truth.
And what's the timeline between the shocks and you measuring the salinity?
Great question. So in the case of the floods, this is going to be any time in the past 20 years you got a flood. So that's going to be kind of a long run type event. In the case of the subtle shock, that's actually going to be contemporaneous. So that's kind of with the water that you would be irrigating this season.
What's the coefficient actually mean here? So I'm confused.
Yep, so this is in terms of salinity unit. So this is the decisiemens per meter. So this is all kind of going to be in the same unit here. You should think about kind of 4, for example, above or below 4 is like really salty or not very salty. Okay.
Sorry, what's the mean?
The true mean, I think, is about, I should have known this. I think it's about 3, I forget exactly. Okay. So the kind of get at the kind of core mechanisms of the, sorry, how much time do I have left? Perfect. Perfect. So to get at the kind of core mechanisms here of how of that model, I want to think about how then that initial change in what you might be thinking changed how you interpret new data. And so to do that, I'm going to combine my survey data with those shocks. So the first question I'm going to ask is what signs you use to figure out how much salt is in your soil. And the prediction of that kind of under identification framework is that if you've had a past experience, that salient shock, that makes you more likely to attribute and think that salinity is a problem, you're going to be more likely to think that low yield, for example, is an indicator of high salinity. So that is indeed what I find. If you've experienced a very salty flood, a very salient event, you're much more likely to attribute this essentially generic signal about how well your crops do to something that has to do with salinity. By contrast, in that kind of subtle shock, we see no effect, and if anything. So that's the first result. The second way we can try to get at this model's predictions is through the diagnosticity of this salinity signals that you actually do treat as salinity. So for example, the way I get at this is through two different survey questions. First, I ask farmers, if you had too much salt on your soil, how would that manifest itself? So what do you think your rice plants would look like? And then the kind of key follow-up is I ask, now, if there's anything else that was not salinity, that would kind of disguise itself to look like salinity. The outcome of this regression is going to be the number of other stuff that farmers say. So it's going to be pests, it could be drought, it could be other things. What you see is that if you've experienced this type of subtle shock, then at the end of the season, you're much more likely to think that the types of signals you might attribute to salinity are actually less helpful for understanding salinity or less diagnostic. So that's going to be kind of very consistent with this idea that you're trying to search for alternative explanations because salinity is less relevant to them. Okay, any questions on these results? Wonderful. So just to kind of summarize here, what I've done in this paper is three things. First, I've shown that there's lots of mistaken beliefs about the environment. So for example, as one benchmark, relative to that threshold of 4, about half of farmers are kind of on the wrong side of that threshold relative to their soil. And the kind of the errors are consistent with some type of identification problem. So the farmers that have more ability to experiment or more experience have better accuracy. Then I've shown that the ways in which you learn are consistent with a model where you can't perfectly identify the signals and how they relate to environmental threats. And so in particular, your initial shock and environmental experience is going to shape how you interpret new data, and that can cause persistent errors. And then finally, in results I didn't show you, I showed that these beliefs actually matter for climate adaptation. So I just want to kind of two conclusion slides. So one, a little bit more speculatively, I want to argue that this result paper shows that kind of just inventing technology itself might not actually be sufficient for coping with climate change if information is incomplete. And so in particular, that implies that there's kind of going to be higher returns to correcting people's beliefs because that also will just increase the value of innovation itself in this space. Second, I want to argue that the types of environmental shocks matter here. And so if flood risk is slowly increasing because the North Sea is getting just a little bit higher every year, but that's not something that's super salient to people in the Netherlands, that's going to be potentially an extremely dangerous type of change in the climate. And then the third thing I want to point out is that climate change is changing lots of stuff. And so one thing that is kind of good news, the bad news about that is that makes it really hard to learn because there's tons of stuff that you have to keep track of. But the good news is that if I give you information about one dimension, so let's say, for example, salinity, in this type of framework, that's going to actually have spillovers on other things. And so you're going to make it easier to learn about pests because now you have better information about salinity. I'm going to conclude just with one quick slide on policy implications. So I think hopefully what I've shown you today is that information can be useful. Perhaps that's not very surprising to economists that giving people information is a good thing. But I think one question that emerges from this is like why wasn't there already a market for this? Farmers have big willingness to pay. I see that kind of 80% of farmers have a positive willingness to pay for information. So why wasn't this already kind of solved by the market? So one explanation is that the individual willingness to pay for information is still only about 80 cents. The cost for me to import one of those sensors is about $70. So kind of for an individual, it doesn't quite make sense for them to buy it. You need to kind of coordinate somehow.
Can they share? So can you move their sensor around?
Exactly. So that's where kind of the spatial covariance becomes important, right? If we can share, but suddenly a player has already purchased the sensor and planted it here, I don't really want to go and buy it now. I just want to ask there and she'll just tell me. And so that's the sense in which this kind of information free riding is going to create an rather inherent problem in this market. So you really need to figure out a way to coordinate.
What you're finding kind of a couple of other ways that you say come up with a
saline tolerant rice variety, they don't know how to infer whether it works, because they're inferring the growth and the non-growth, but these varieties would signal something else.
That's right. Yeah, I think, I think there's, I'm not gonna say that farmers can't learn when they experiment well. But yeah, that is a good point that like it's hard to learn just from one draw, because also lots of other things, say I planted a rice, a tolerant seed and it fails, it could be because of pests, and that might be a big part. So that's exactly right. That makes sense. So I guess just wanted to, with my last minute, point out that so one policy question then is, can my information experiment that seemed to be successful be scaled up cheaply? And one way I get at that is I randomize the type of information I provide farmers. So I either give them aggregate information, so I say of the 90 villages around you, this is the average salinity, or I give you information just about yourself. And so in that aggregate information, this is the willingness to pay. So I'm not giving you any information about your own plot. If I give you also information about your own plot, you see that these willingness to pay curves are essentially indistinguishable. So the good news is that farmers seem to recognize that there's high spatial covariance, and they don't care about whether you go measure their own plot. So it actually means that we don't have to go and measure every single farmer's plot. That's going to be really, really expensive. We can just go measure a couple plots in every village, or even at a higher level, and that will still be useful to farmers. And so I'll allow you to say that this kind of insight about how the types of past shocks impact your beliefs also allows us to target better. We might not have to go to villages where we think everyone is, has right beliefs or is kind of wrong in some ways the right direction, and we can help target more judiciously. Okay, thank you all so much. This was really fun. Thank you.
We're gonna go on break. We'll be back in 11.